Our topic today is something that many students often find challenging, but we're going to break it apart into small enough chunks that I think you'll get it. The overall topic we're going to be discussing is the idea of mass ratios, and we'll start with a pretty simple concept called percent mass, and then we'll use that percent mass to deduce empirical formulas for compounds, and then we can also determine molecular formulas using empirical formulas in molar masses. Now, if you're not sure what this means right now, that's fine. We'll go through it slowly enough with enough examples that I think you should be able to get it. Let's start with an analogy that we've seen before. We said that if you wanted to know how much the different components of a human body were, you could just take one component at a time, the brain, the heart, and the remains, for example. And if you add up all those three things, you should get the total weight of the human body. And by analogy, we could do the same thing for the weight of a compound. We said if we want to know the mass of calcium nitrate, we would just add one calcium weight. That's the atomic weight of calcium, 40.08. And then the weight for nitrogen is 14.01, and we have to multiply that times 2 because there are 2 nitrogens in this formula and 6 oxygens. So we take 6 times the weight of oxygen, and adding all these things together, we get the total mass of calcium nitrate. So this part is hopefully a review. We're going to take it a step further now and start extending our thought experiment and say, what is the percent of the mass of a human body? What percent of that is brain? So if we go back to look at our slide and see a brain is 6.36 pounds, the whole body is 190.9. We want to know what percent of the body is brain. We would take the mass of the brain, divide it by 190, the total, and because it's a percent, we multiply times 100, and that gives us about 3.3% brain. So that's pretty good brain matter, pretty good amount. We can use this analogy to ask what percent mass of some compound is a given element. So for example, what mass of nitrogen what's the percent of that in calcium nitrate? So just like we isolated one element of the human body, the brain, to get a percent, we'll isolate one chemical element in this whole compound to get a percent. So for nitrogen, we have to look at the mass of just the nitrogens. Remember, there's 2 of them. So we multiply it times 2, divide that by the total weight for the whole compound, multiply times 100, and we get 17% nitrogen. So of this whole compound, about 17% of it is the element nitrogen. So you might wonder, what is this good for? And it's good for a lot of things. One of those things is identification. So let's say you are in a forensics unit and you go to a crime scene and to collect some unknown substance, and you're not sure what it is, but you think it might be methamphetamine. So how could you test it to see if it's methamphetamine? Well, you can measure the percent of carbon in it. And if you did that for this unknown substance and you find it's 80.49% carbon, you could ask yourself, might it be methamphetamine? So how could we do that? Well, let's look at methamphetamine and see what percent of it is carbon if the total mass is 149.223 grams per mole. So to do this, we'll get 10 carbons times the mass of carbon divided by the total mass of the whole thing times 100, and we get 80.5%. So this looks like we can use it to get an indication of what our chemical substances are if we're not sure what they are. So this is one good application for it. Now, one thing that's useful once you get mass percents is that you can use them as conversion factors. So let me show you an example. This is a real example from a textbook that uses percent mass. The question is, if someone consumes 22 grams of sodium chloride, NaCl, per day, what mass of sodium does that person consume? And they say sodium chloride is 39% sodium by mass. So let's rewrite 39% sodium as a conversion factor. So there's 2 ways to write it. You could say 39 grams out of 100 grams of sodium chloride is sodium. Or you could say, you could flip the ratio. In 100 grams of sodium chloride, 39 grams is sodium. And either way this ratio works is fine. You could write it either way and it would be completely correct. So let's go and try to answer our question. It said if we ate 22 grams of sodium chloride, how many grams would be just sodium? So we need to multiply by one of these two conversion factors. And let's pick which one we want. If we use this first one, we'd have 100 grams of sodium chloride on the bottom of the fraction, and that would cancel grams of sodium chloride and give us grams of sodium. So that's the one we want. Let's use that. And if we do that, we'll see we're consuming 8.6 grams of the element sodium. Now I point out this example because it's actually a little funny. Whoever wrote this wasn't thinking very clearly about whether or not it was safe to consume 22 grams of sodium chloride. So to put this in context, if you see how much salt is 22 grams of salt, if you ate a McDonald's quarter pounder with cheese, you'd only be eating 1 gram of salt. So to get 22 grams of salt, as this question suggests you might, you'd have to eat 22 quarter pounders with cheese. This is not a healthful decision. Don't do this. The U.S. recommended daily allowance is less than 2.3 grams of salt per day. If you eat much more than that, you could get high blood pressure, stroke, or kidney disease. So my point is, take some of these problems in your textbook with a grain of salt, and I guess that pun was intended. So let's talk about percent mass with hydrates. We mentioned in a previous video what a hydrate is, and to remind you, it's just a crystalline substance that has water intercalated in part of the crystal. So an example is copper sulfate. Usually every formula unit of copper sulfate has 5 waters stuck inside the crystal. So previously we calculated the mass of just the copper sulfate part. That's 159.609 grams per mole. The water, there's 5 of them, so we multiply the mass of water times 5 to get the mass of the whole hydrate together. Now you can use this percent mass idea to say what percent is the water in this whole crystal. And to do that, you take the total waters, 5 times 18, divide it by the total mass times 100, and you see that this crystal is really about 36% water. Now, if you want to know how much water is in a crystal, you can actually heat it. You could weigh it and then heat it and see how much water you lose as you heat it, because water turns into vapor and it escapes. So an example of that type of problem. If you had, let's say, 15.67 grams of a hydrate of magnesium carbonate, and here's the formula weight for just the magnesium carbonate part. You heat it to drive off all the water, and here's the molar mass of water. You would reduce the mass to 7.58 grams. So it started at about 15 grams, you end with about 7 grams. And this information alone can tell you the formula of the hydrate. Now, what's our first step? What are we going to have to do? We're going to have to determine how much water was driven off. We'll have to look at the mass. And then we'll have to find out how many moles were magnesium carbonate and how many moles were water. And then once we do that, we can find a whole number ratio between the water and the magnesium carbonate. So let's go back to step 1. Let's find the mass of the water that was driven off. Well, before we heated it, its mass was 15. After we heated it, it was 7. So what was lost when we heated it? Just the water. So let's find the difference between 15.67 grams and 7.58. And that tells us that there were about 8 grams of water that we were heating and were driving off from the hydrate. So now we've got grams of water. This 7.58 is grams of just magnesium carbonate. That's the only thing that would be left after we heated it. So we've got grams of a substance. Can we now convert to moles? And I think you know the answer is yes, we can. Let's do the magnesium carbonate first. We had 7.58 grams of it left. Here's the molar mass of magnesium carbonate, and that tells us here's how many moles of just the magnesium carbonate we had. Let's do the same thing with the water. Here's our mass of water, 8.09 grams. So we'll write it down here, divide by the molar mass of water, and we get the moles of just water that were there. So now what are we trying to find? The formula of the hydrate. What is the formula going to look like? It's going to be a ratio of the water to the magnesium carbonate. So let's get a mole ratio between the 0.449 moles of water and the 0.0899 moles of magnesium carbonate. If we divide the moles of water, 0.449, by the moles of magnesium carbonate, we get 5. And the moles of magnesium carbonate ratioed to itself will of course just be 1. So what does this tell you? It says that for every 1 mole of magnesium carbonate, you had 5 waters. So that means this is magnesium carbonate pentahydrate. That would be the formula for this hydrate. And it would look just like this. Now the little dot means that the water's not chemically bound to it, it's just physically stuck to it inside the crystal. That's what that little dot means. Okay, we're going to move on to talk about something called elemental analysis. It's a technique to try to figure out what elements are present in a sample and what their mass percent of each element is. And the idea is that we can obtain a chemical formula for some unknown sample if we do elemental analysis. Now the instrument itself looks like sort of like a big washing machine. And what you do is you stick your sample inside and you burn it with a known amount of oxygen, and you measure how much carbon and hydrogen and water and CO2 comes out of your sample. Now if you do that, what can you get? For example, you put an unknown sample inside your elemental analysis, and what it will tell you is that you have, for example, 25.2% hydrogen and 74.9% carbon. And is that useful for anything? Well, it turns out you can actually use this to get a chemical formula. What is a chemical formula? It's going to be the elements that are present with the mole ratios, the whole mole ratios that would tell us the formula. So, for example, we could determine that something with 25.2% hydrogen and 74.9% carbon has this formula, CH4. Now, I'll show you the method to do it, but it's tedious. I'll warn you in advance, it's tedious. So to give you some incentive to understand why we're doing it is that this is actually a tremendously powerful technique. And to illustrate its power, I will tell you about this picture. This is a picture from the cover of a scientific journal called Physical Chemistry, Chemical Physics. And what's illustrated on this cover is the chemical structure of a compound called Taxol. And Taxol is a multi-billion-dollar blockbuster chemotherapy drug. And it's tremendously active against breast cancer in particular, but many other cancers as well. And for a very long time, the actual chemical structure of it was unknown. The reason this is on the cover of this journal article is because a researcher named James Harper was able to figure out its structure and published it in the journal. And a major key piece of evidence he used in determining this structure was elemental analysis. So this is a real relevant science technique that's used in cutting edge research even today. So let's get through the tedious bits of it. Let's do this with looking at an example. Suppose you want to determine the empirical formula for para-amino-benzoic acid. So you subject it to elemental analysis and you find it's 61% carbon, 5% hydrogen, 10% nitrogen, and 23% oxygen. So if our task is to find the empirical formula, we can start by writing sort of a skeletal structure for it, just the elements that are present. But we don't know the mole ratios yet. We'll say the mole ratios are X, Y, Z, and Q. We've got to find those out. So the next question is, how do we do that? Well, we're going to find these small whole number ratios by using the percent masses that were given to us. And the easiest way to do that is to ask ourselves, what if we had a 100-gram sample? If we had a 100-gram sample of this compound, and 61% of those 100 grams is carbon, how many grams of carbon would that be? Well, 61% of 100 grams is 61 grams. 5% of 100 grams is 5 grams. 10% of 100 grams is 10 grams, and so on, so you get the idea. So if you've got your grams of carbon, hydrogen, nitrogen, and oxygen, and what we're after is moles, what we're going to have to do is convert all of these grams to moles. And I think you can do that, and we'll get some more practice doing that right now. So we'll take our grams of carbon that we've got, divide by the molar mass of carbon, and we get 5.105 moles. And what we were after was a mole ratio for carbon, hydrogen, nitrogen, and oxygen. So let's take this moles that we have here, and plug it in for the moles of carbon. And we'll put it there like that. Now, you might have an alert going off in your brain and saying, wait a minute, these are supposed to be whole number ratios, and I promise you I haven't forgotten that. We'll get to that, but for the sake of getting through this problem, let's just carry on and we'll see what happens. Next, we need to find the moles of hydrogen. So let's take the grams of hydrogen, divide by the molar mass of hydrogen, and we'll get 5 moles of hydrogen. So let's plug that in to our formula here. And of course, next we have nitrogen. Let's take our 10 grams of nitrogen, divide by the molar mass of nitrogen, and there's our moles of nitrogen there. And last, of course, is oxygen. 23 grams of oxygen converted to moles, divide by the molar mass of oxygen to get the moles. So now we have something that looks a lot like a formula that we need. It's got all the elements and it's got moles for them. But an empirical formula, do you remember what an empirical formula is? It's the smallest whole number ratio. And what we have right now are not whole numbers. But we could get a whole number ratio if we divide every one of these moles by the smallest amount of moles. That would give us at least one whole number. So let's get our empirical formula by dividing all of these by the moles of nitrogen. Why the moles of nitrogen? Because it's the smallest, and because it would give us at least 1 mole here, a 1-to-1 ratio here. So if I divide all of these numbers by the moles of nitrogen, let's see what we get. We get something that looks like this, C7H7N1O2. Are those small whole number ratios? And the answer is yes, yes they are. Now if we have 1 mole in the mole ratios, we don't usually explicitly write it, so here's really what the empirical formula would look like to us. Now, did we get it right? That's the next question, of course. So let's have a look at the structure for para-aminobenzoic acid and see if we got it right. There's 1, 2, 3, 4, 5, 6, 7 carbons, 7 hydrogens, an oxygen here and here, and a nitrogen. So yep, we got it right. That's how you do it. And that's the compound that you find in old sunscreen. This is a UV absorbing compound, and we can get the empirical formula of it just from the percent masses. Now you might say, great, we got an empirical formula, but there's many cases where an empirical formula is not the same thing as a molecular formula. So let's just think about what the distinction is. If you had this white substance with 4 phosphorus atoms and 10 oxygen atoms, you'd have a molecular formula for it called P4O10 tetraphosphorus dicoxide. And if you add up all the 4 phosphoruses and the 10 oxygens, you'd get a molar mass that looks like this, 283.886 grams per mole. Now, do you remember how to get the empirical formula? To do that, we need the smallest whole number ratios between the phosphorus and the oxygen. So how would we get that? Well, to get the smallest whole number ratios, we'd have to divide both of these by 2. So that would give us a ratio of 2 to 5, and we can't get any smaller whole numbers than that. Now, just for the sake of this thought experiment, let's calculate the mass of this thing, P2O5. It's 2 phosphoruses, 5 oxygens, and we get this mass, 141.953. So my question for you is, how is the molar mass of the molecular formula related to the molar mass of the empirical formula? Let's do a ratio of those things. The molecular weight to the empirical formula weight, we just plug in 283 on top, 141 on bottom, and we get a ratio of 2. Where does that 2 come from? Well, that's the number we had to divide by to get from the molecular to the empirical formula. So by finding the ratio between the molecular formula mass and the empirical formula mass, we can go back and forth between those two things just by knowing that factor that we had to divide by. So let me show you an example. Let's suppose we do elemental analysis on an unknown pollutant, and we find that the empirical formula is CH just from that. And using a technique called mass spectroscopy, we find that its weight is 78.1134. So what is the molecular formula? If this is the molecular formula weight, but its empirical formula was just CH. So what are we going to need to do? To go from our empirical formula to our molecular formula, we need some factor, the ratio between the empirical formula weight and the molecular formula weight. Well, how did we get that before? We took the ratio of the molecular weight to the empirical formula weight. So let's try that. To get that ratio, here's the molecular formula weight, 78, divide by the empirical formula weight, 13, and you will get a factor of 6. So what does that tell you? That tells you that the molecular formula is 6 times more massive than the empirical formula was. And that tells you that our compound is C6H6, and if it was this pollutant benzene, then we would have figured out the actual molecular formula for it. And that is the amazingly powerful way to take percent mass data and turn it into an actual chemical formula.